Okay. So today we shall be doing matrix pseudo-inverse and linear systems. Before we begin formally, you already know this, but keep this in mind. Derivative of a constant is 0. Derivative of P transpose X is the same as derivative of X transpose P, which is P. Remember, this has to be a row vector, a column vector. Quadratic function, the derivative of X transpose QX is Q plus Q transpose X. We are making this Q into a symmetric matrix here. Q plus Q transpose is symmetric. And when, by default, Q is symmetric, then derivative of X transpose QX is twice QX, and the second derivative is twice Q. Okay, now conditions at the minima. Suppose we have this function, it's a multivariate function, it takes a vector argument, but produces a scalar. Okay, so it's a mapping from n dimensions to one dimension. And let's suppose X star is the minimum, unconstrained minimum, okay, of phi of X. Then the conditions for this to be a minimum are the first derivative should be equal to 0. At the minimum, this is common sense, and this is a necessary condition. The second derivative of phi of X should be positive definite. This is a sufficient condition. Suppose this is not positive definite, but positive semi-definite, it still could be a local minimum. Okay, this is the first order necessary condition. This is the second order sufficient condition. Now, suppose we have, in addition to the function, we have to do the minimization subject to this equality constraint. Okay, in this case, X star is argmin of phi of X subject to Ax equals B. Okay, here how do we do the minimum? You might not know this, but we use this in this lecture. We construct a Lagrangian function, and it contains X and it contains mu, which is a dual vector or variable. Okay, X and mu. So we have a primal variable and a dual variable. And so phi of X, which is the function that we're trying to minimize. And then this is what we do. Mu is a vector, column vector. So mu transpose of Ax minus B. This constraint is equivalent to Ax minus B equals 0. So this I attach to my phi of X, and that gives me the Lagrangian or Lagrangian function. And mu is called the dual variable. Okay, and if you look at the analogy, once you construct the Lagrangian, you can write down the first order and second order conditions. The first order condition is at the optimum. Now we have to optimize with respect to mu as well. Okay, at the optimum, derivative of L with respect to X equals 0. This is the first order necessary condition. And the second order sufficient condition is this. Second derivative of L should be positive definite. If it's positive semi-definite, it still could be the constrained minimum. Okay? Keep these in mind. Okay, so what we shall do in this lecture is I'll first give you an exposition to the Moore-Penrose pseudo-inverse. I'll just refer to as the pseudo-inverse of a matrix. And then we'll look at overdetermined systems I'll give you an example of where it's applied, overdetermined systems, and we'll be looking at all these in details. And then an underdetermined system, and I'll give you a probabilistic explanation of why we take that particular approach. Okay, so first, just an overview. So this is what we have: m equations and n variables, and m and n might not be the same. They could be different. And we have to solve Ax equals b, where A is a m by n matrix, x is a n-dimensional vector, b is a m-dimensional vector. The solution is x equals A plus. So this A plus is the Moore-Penrose pseudo-inverse of A, and it has the dimensions of the transpose of A. Okay, so A pseudo-inverse B. See, if A is a m by n matrix, then A pseudo-inverse is a n by m matrix. Now, when m is greater than n, okay, so we'll assume that the rank of A is n. It cannot be more than n for obvious reasons. So we'll assume that it's full column rank, full rank or full column rank, which is n. And in this case, x equals A pseudo-inverse B is an approximate solution. And the A pseudo-inversion, the formula is this. A pseudo-inverse is A transpose A whole inverse A transpose. The rank of A is n, right? Therefore, A transpose A is a n by n square matrix. It's invertible. So A transpose A is an invertible matrix. So this expression holds. Now, when m is less than n, then we say that A is a wide matrix, in which case the rank of A cannot exceed m, the lower of the two. We assume that rank of A is m. In other words, A is a full row rank matrix or full rank matrix. Again, the solution is x equals A pseudo-inverse B, but this time it is the exact solution. And here, A pseudo-inverse is A transpose times A transpose whole inverse. The rank of A is m, correct? Since m is the smaller of the two. What's the dimension or the size of A transpose? M by m, right? So it's a smaller matrix, and obviously, under this assumption, the rank of A transpose is m. In other words, it's an invertible matrix. So this expression holds. Notice the difference between this case. Here we are inverting A transpose A, and here we inverting A transpose. Okay. Now, when m equals n, in that case, both of these expressions reduce to A inverse. Okay, because if A and A transpose are both square matrices, then you can open up the parenthesis, swap the A and A transposes, and so you have A transpose inverse A inverse. And here you would have, again, open up the parentheses, first take A inverse, then A transpose inverse A transpose. Okay, and then it simplifies to A inverse. So both expressions are valid, and they reduce to A pseudo inverse equals A inverse when m equals n, and that we've seen before. Okay, so now we'll take up these two cases separately. First, we focus on overdetermined systems. So we have m equations in n variables, and m is greater than n. Okay, so these are my equations, linear equations, How many equations do I have? M equations. M as in Maryland. And how many? So I have B1 through Bm here. All the A's are the coefficients. And how many variables do I have? X1, X2 until Xn. N as in Nebraska or New York. Okay, so we have more number of equations to satisfy than the number of variables. We cannot find an exact solution. Okay, anyway, I'll write down the ith row. This is the general ith row, a I1 x1 plus dot 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 until a I n xn equals bi, the ith row somewhere here. Or this is the expression for the ith row. Summation over j, aij, xj equals bi. Okay. And like I said, since we have more number of equations than the number of variables, we cannot simultaneously satisfy all these equations. Right? So our objective is to try the best approximate solution. In vector matrix form, this is what it looks like. I arrange all the coefficients as a matrix, and this is the variable vector now, x1 through xn, and then this is my right-hand side scalar, vector. Visually, this is what it looks like. And here, A is a tall matrix. Okay, it's a tall matrix because M, the number of rows, is more than N, the number of columns. And we assume that the rank of A is this N, N as in New York. And so since we cannot satisfy exactly, what we do is we will try to find an approximate value x such that Ax is as close to B as possible. Okay. Now remember, this is the ith row, and I multiply it with all the x's, and I get the ith entry in B here. Okay. And I have to make, for each row I have to make summation aij xj be approximately equal to bi. Okay, this is where we are. And so let's take the difference between the two, Ri. This is the difference. We would like to make the absolute value of Ri as small as possible, correct? So Ri is the error, also called the residual. Okay, I'll just call it the error. So this is the error between Bi and summation aij xj. Okay, if I write all the errors, because I have, this is for the ith row, I have m rows, so I have a vector of errors R1 through Rm. And this is the notation, by the way, I'll follow. Ri, I equals 1 through m. It means that a column vector of R1 through Rm. Okay, therefore, R equals B minus Ax. Okay, and what will we try to minimize? Should we try to minimize summation of the Ri's? No, because this can be positive or negative, right? So one option would be to take the absolute values and then try to minimize, but then absolute value introduces a discontinuity. So the best approach is to construct this function here, phi of x equals summation Ri squared. This is nice differentiable, Ri squared. Or in vector matrix form, this R, phi of x is R transpose R. Okay, this is the square normed error, because R transpose R is the square norm, right? L2 norms of R squared. It's also the sum squared error, because this is, if you look at the scalar version, this is a squared error for the ith row, and I'm taking the summation of that. So sum squared error or square normed error mean exactly the same thing. Okay, so this is what I want to minimize. R transpose R, where R equals B minus AX. Okay, so this is where we are. Phi of x is R transpose R. And since R is B minus AX, we get this. And I open up the parenthesis here. So I get B transpose B, then I get AX transpose is X transpose A transpose B, then I get B AX, so with a negative, B transpose AX, and then X transpose A transpose AX. This is a scalar, right? R transpose R is the squared L2 norm. Each of these is a scalar. Okay. Now, a scalar transpose is equal to the scalar itself, right? So B transpose AX is the same as X transpose A transpose B. So I can replace these two with X transpose A transpose B with a 2 here, because both these terms are the same. Okay, so this is where we are. So what's the derivative of this? B transpose B, let me differentiate this with respect to X. What's the derivative of this? 0, because B is a constant, it's given, right? It's not a function of X. Derivative of this is, note that A transpose B is a vector. Correct? So what's the derivative of twice X transpose P, where P is a vector?
X.
No. Derivative of X transpose P is P.
Yeah, sorry.
Right? So, and what's the derivative of this? This is a matrix, and it's also positive definite, by the way, right? I meant it's full rank, but yes, it is positive definite. So the first derivative is this. And this is the second derivative. A transpose A takes the place of Q in the first slide. Okay. Now, at the minimum, this is what we should have, right? This is simple minimization. At the minimum, the first derivative is 0, and hopefully the second derivative is positive definite. Okay, now the second derivative here is positive definite. A transpose A, we learned from Cholesky decomposition in the last lecture that it has to be positive definite. Okay, so it is positive definite. And so we have to take care of this first derivative being equal to 0 and solve for x. So del phi of x star, where x star is the minimum, is equal to 0. Whence, note that we have 2 and 2 common here, and we have a negative sign. So from this expression, we get A transpose A x star equals A transpose B. Whence, since A transpose A is full rank invertible, so x star equals A transpose A inverse A transpose B. Now, let's look at this equation. This is the final equation that we are looking for. Okay, x star. We got the solution x star. But let's look at this, equation 2. What's A transpose A? What size matrix is it? N, right? So here we have, and X is n dimensions, right? So we have here, if we break this down into scalars, how many rows will we have? N as in New York, n rows, and n variables. correct? And here, A transpose B, the right-hand side, instead of M as in Maryland, it's now N as in New York. Okay, so remember this expression, okay? So this is where we are, overdetermined system. We have M equations in N variables where M is greater than N, and so we cannot find the exact solution. We try to find the approximate solution, and this is visually what it looks like. A transpose A is this small matrix, and it is full rank invertible. What we try to do is we try to minimize the L2 norm of B minus AX whole squared, which is R transpose R. And this here, these are the set of equations that we get. This is an important expression independent of the next two. A transpose A X star equals A transpose B. This we can solve directly, right, using any of the previous approaches, LU decomposition or PLU decomposition, because we have N variables and N linear equations. Okay. Alternately, we can say X star equals A pseudo-inverse B. And this is the expression for the pseudo-inverse. This is when A is a tall matrix. Okay, and so this is, you can verify yourself that A pseudo-inverse A equals the identity matrix. Okay, A pseudo-inverse A is the identity matrix. But A pseudo-inverse is not an identity matrix because it cannot be full rank. Right? The A pseudo-inverse will give you a M by M matrix. M as in Maryland. It will give you a square matrix, but of size M by M, the higher of the two, M and N. Okay, but the rank will be N, the lower of the two. So obviously, it can never be equal to the identity matrix because it's not even full rank. Questions? Yeah.
My question is that if we have M equations and N variables, and equations are more than variables,
yes,
then in linear systems we have read that if we have N variables, unknown variables, we must have N equations, at least N equations. It should be equal to number of variables.
What do you mean by at least then?
To find the unknown variable.
The number of equations, you said that it has to be at least N, which means it can be more, which is...
It can be more.
Right.
So if we have more equations, then we can just drop the rest of the equations.
No.
What?
Because pick which equations you want to drop, and each time you'll get a different solution. Because it's full rank, it's full, here I said, M is more than N. Yeah, it's, oh, I see what you're saying. What you're saying is, this is full column rank. So you'll have dependent variables, correct? Now, what will happen then, you will be placing more importance on some equations than the others. Suppose, simple case, suppose the first N equations are fine. And then N plus 1 through M, all those equations are repeat of equation 1. Okay. Suppose that's what they are. Now, when you reduce them, you might get, place a higher weightage on this one. Right? And so it depends on how you do the row reduction. Okay, each time you have to do some multiplication. Each row you have to multiply and then do some row operations. It depends on how you are doing the row operations. According to that, you'll get different weights. But I still see your point. It's a little hard to explain, but I will write it down later on. What would happen is you would be pre-multiplying this with a or should we say, yeah, pre-multiplying this with a vector transpose, okay? And then you will see that you will get different solutions. It will depend on what you are pre-multiplying this with. Okay, so you're pre-multiplying this with a matrix actually, m by n matrix, okay? M by m matrix. And then this matrix times this, let's call this B. B times A would be a n by n matrix. So B is n by m, and this is m by n. Okay. So it depends on what you're multiplying this with. I'll show that to you. Now, the very good approach is this. This is in fact what we are doing. Instead of taking some B just to reduce the number of rows, okay, we are multiplying it with A transpose. That's a very good logical choice, right? We can take some other matrix B here, but then.
So in this, since it has infinite number of solutions, we are choosing the one which gives the least distribution.
Exactly. Okay. I hope that answers your question.
Yes.
Perfect. Okay. So, approaches to overdetermined systems, and I'll give you an example too. Okay. This is the overdetermined system, and one way to approach this is reduce the m equations to a set of n equations by row operations. Excuse me. So A transpose AX equals A transpose B. Okay. How do you solve this? What's the best way to solve this? Hint, not LU decomposition or PLU decomposition. Why? Because A transpose A is, we know, it's a positive definite matrix. Correct? And so, the easiest approach is, if you don't have a subroutine to compute the pseudo-inverse, then do Cholesky decomposition. A transpose A is equal to LL transpose, so that we have LL transpose X equals A transpose B. And then X equals L inverse transpose, L inverse A transpose B. And we know that inverting a lower triangular matrix is an easier task than inverting any matrix in general. So this is one method to do it. Otherwise, we can use the pseudo-inversion formula itself. X equals A pseudo-inverse B. Now, let me tell you this. The numerical subroutines, I don't know what MATLAB exactly does, but numerical subroutines don't, if there's a subroutine for pseudo-inversion of a matrix, it'll most likely, I'm almost certain that it will resort to something called singular value decomposition rather than doing Cholesky decomposition because of numerical stability reasons. Okay, and we haven't done SVD or singular value decomposition yet, but we'll look at it later on. So most likely pseudo-inversion to to do pseudo-inversion, subroutines, inbuilt subroutines don't use Cholesky decomposition. They actually use SVD. And another method is QR decomposition, which we shall address in the next lecture. So here is an example, a simple example, and this will make the point clear. We want to solve AX approximately equal to B. This is what we have. We have 3 equations in 2 variables, x1 and x2. What we do is we can reduce, this is a rank 2 matrix, so we can eliminate rows different ways. We can do the elimination according, and we can choose this, pre-multiply this A with any matrix, right? But what we choose to do is use this. This is what the the min norm or minimum of the sum squared error solution would yield. So it would be the same as solving this equation. A transpose AX equals A transpose B, or this. So I have a quick and easy way to solve it now. This is equal number of variables and equations. And so I invert this, and this is what I get. Okay? Now here's an example of where experimentally you would like to solve overdetermined systems. Truck moving with a uniform acceleration. Okay. Now we know from physics that the displacement at any time t is the initial displacement plus initial velocity times t time plus half acceleration t squared. Or y, the displacement at time t, is y naught plus v naught, initial velocity times t plus half acceleration times t squared, right? Now, we can rewrite this as, we don't know what these values are, initial displacement, initial velocity, and acceleration. We don't know. These are unknowns, okay? So this is what we have. And the unknowns are, in general, this is the form, right? Alpha naught, alpha 1, and alpha 2 are the unknowns. This is what we want to find. Suppose we have 100 observations at different, like the truck is going at uniform acceleration. That's all we know. Okay, and then we take 100 samples, and each time the displacement of the truck, where the truck is in the highway. Okay, T1 through T100, the positions of the truck or the displacement of the truck is y1 through y100. So what we have is, we would try to fit each of these sample points. We have 100 sample points, and we should fit each of these sample points. So y1 is alpha naught plus alpha 1t plus alpha 2, alpha 1t1 plus alpha 2t1 squared, right? And likewise for y2 until y100 equals again alpha naught, alpha 1 t100 plus alpha 2 t100 squared. Now these t's are part of our sample, right? So they are known, numerically observed, right? The y's are known. You might think that y's or t's are the variables. No, here y's and t's have been observed, right? So they are fixed. We know their numerical values. The variables here are actually the alphas. Don't get confused here, okay? The variables are the alphas. That's what we want to find out. Okay. In general, we have, let's say, m samples, t1, y1 until tm, ym. Okay, and we want to fit, instead of a quadratic, we want to fit an n minus 1th order polynomial. So we want y equals alpha naught plus alpha 1t plus alpha 2t squared until alpha n minus 1 t to the n minus 1. We want to fit this polynomial, and this is the set of samples that we have. We have plenty of samples, okay? And the polynomial is, it's a low rank polynomial, quadratic or cubic or something. Okay, so n is less than m. How many variables do we have? The variables are alphas, alpha naught, alpha 1 until alpha n minus 1. Okay, so we want to find these alphas that would best fit these observations. And these are the unknown variables, alphas. Okay, the t's and the y's are all known. This is an overdetermined system. The first observation yields this, second, and all the way until the mth observation, sample observation yields this equation. Okay, so this is what we have. Vector matrix form, it reduces to this. This matrix is known because the t's are part of our samples. The y's are also known. These are all part of the observations, and we have to solve for alpha. So we have V alpha equals y. V is a m by n matrix. See, this is t to the 0, this first column, then t to the 1, t squared, until t to the n minus 1. Okay, so m as in Maryland by n as in New York. That's V. It's called a van der Monde matrix, by the way. A matrix of this form is called a van der Monde matrix. Vandermonde. So this is what we have, and the solution is alpha equals V pseudo inverse y. Okay? This is the van der Monde matrix. Any other questions? Okay, underdetermined systems. Now we'll look at the opposite case. We have again m equations and n variables, but this time m is less than n. So these are the linear equations that we have, and we have m number of equations and n number of variables, but m is less than n. So it means that in theory we have an infinite number of solutions, right? So how do we approach this problem? Now, this is the ith row, of course. So we have multiple solutions. In fact, we have infinite solution. Okay, so how do we formulate our problem? Okay. Okay, so this is what it looks like in vector matrix form, and visually this is what we have here. The matrix A is a wide matrix. It has less number of rows than columns. We have plenty of variables to choose from. Okay, how do you solve this? So now we have plenty of solutions that would exactly match. Ax would equal to b, correct? So which of these should we choose from? Ax equals b, we can trivially satisfy with so many possible values of x. We want to find the solution that minimizes x transpose x. It's the min norm solution. Okay. Minimum of L2 norm of x squared is what we want to minimize, and I'll give you a theoretical reason why. So this is what we want to minimize. In terms of scalars, well, I'll just arbitrarily put a half here. Okay. And so we want to minimize half of summation xj squared subject to, for each rho I, we must have summation Jij xj minus Bi equals 0. This is the symbol for all. So for all rows I, we must have this equality to be satisfied. Okay. So we form the Lagrangian objective function, and then for each of the scalar constraints, I multiply it with a mu I, a dual variable, and take the summation of that. So this is my Lagrangian. In vector matrix form, this is what I have. Minima is half x transpose x subject to Ax equals B, and so this is my Lagrangian. Lx mu equals half x transpose x plus mu transpose times Ax minus B. Okay? And what's the dimensionality of this vector mu? Here, how many i's do we have? 1 through m. M is the number of rows, right? And so we have m as in Maryland number of constraints. So mu is m dimensions. Any questions so far? And we note that what's the first derivative of this Lagrangian with respect to x? X plus first term when you open it is mu transpose Ax, that will give you A transpose mu. And the second derivative is, what's the quadratic here? X transpose Qx is, what's Q here? It's I, the identity matrix. So the second derivative is the identity matrix. Okay. And we know that we have to satisfy these conditions. This condition, this is a necessary condition. The first derivative should be equal to 0. And we should also have Ax equals B. That's a necessary condition. This is a sufficient condition. Okay. But if you're lucky, the sufficient condition will also be satisfied. What happens here? The sufficiency condition is satisfied because the identity matrix is positive definite. We know that. So I'll ignore the second order sufficient conditions from now on. I just took care of it. Okay. So these are the remaining what we have. First, let's look at the first derivative of L. This is x plus A transpose mu, and we know that at the optimum, now the optimum also should have a value of mu, okay, because now we have more number of variables. Okay, so x star mu star is the optimum, the minimum. Okay, now, so at the minimum, we have x star plus A transpose mu star equals 0. Whence x star equals negative A star mu. So from this equation here, the first order necessary condition for constrained minimum, I got this expression here. So this is now taken care of. Okay. Now I only need to make sure that Ax equals B. This is what I get. X star, is equal to negative A transpose mu. Let me get this expression here. Ax star equals B. Okay. X star is equal to this. Whence I have negative A transpose mu star equals B. Whence mu star, just solve this, mu star is negative A transpose inverse B. This is my A transpose. It is fully invertible. It's a N as in New York by N as in New York square matrix. Okay. So I get my mu star. And now I can easily get my x star from this expression. So x star is this. Two negatives cancel out. I have A transpose inverse B. So this, in summary, is what we just saw. Ax equals B, we want to solve. It's an underdetermined system. And so this is a wide matrix. And so we are going to look for this. We want to minimize the min-norm solution. And so these are the expressions that we get. X star is a pseudo-inverse B, where a pseudo-inverse is given by this expression here. Here, A is a, what's the rank of A? It's N, right? No, it's M, the lower of the two, M. So a pseudo-inverse will be a M as in Maryland times M as in Maryland square matrix, right? And you can check it's equal to the identity matrix. So a pseudo-inverse is the identity matrix. In the previous case, for overdetermined systems, we had a pseudo-inverse times A was the identity matrix. Okay, so it's the reverse now. A pseudo-inverse is the identity matrix, but A pseudo-inverse A would be a bigger matrix. It wouldn't be full rank, so it can never be equal to the identity matrix. Questions? Okay, now the question is, why did we try to minimize this? Okay, that's a little beyond this course, but it's good to know. It's very important in deep learning. One of my areas is deep learning, data science, so it's very important in deep learning, by the way. Okay, so these are my set of equations. M equations and n variables. And m is less than n. Now, let's concentrate on xj. Do you think what's more likely? Should xj be positive or negative? We have no idea whether the coefficients a's are what are positive, what are negative. On the b, we don't know what's positive, what's negative. They're equally likely to be positive and negative, the a's and the b's. So what is more likely? Is a more likely to be positive or more likely to be negative? Or are they equally likely? Without any prior knowledge of A's and B's, xj is equally likely to be negative or positive, correct? So it's symmetrically distributed around the origin. Now, again, with no knowledge of the values of these A's and B's, okay, what's more likely, x is 1 or x is 1 billion? Which is more likely? Or 1 trillion, on an average problem. The numerical value can be anything, right? It could be very small, it could be very big, right? Now, a safe assumption is the higher the value of x is more unlikely. It's very unlikely to be like 10 to the 50. It's much more likely to be 10 to the power of -1 than 10 to the power of 50, right? So under these circumstances, we can assume that xj, each xj follows a Gaussian distribution. Okay. Now, okay, so this is a Gaussian distribution.
It means we are just trying to say that we have infinite solutions in this underdetermined system, but the solutions of higher numbers or a very low number is the probability is less.
Sorry, I couldn't get it. The probability of low numbers are higher than probability of high values of x.
No, a very, very low number, like nano, micro, nano.
It could be 0, because x could be 0.
Yes.
Okay, and there is an interesting point here. From information theory, the safest assumption is that it's a Gaussian distribution. Okay, that means you make no other, without making any other assumption, the safest approach is Gaussian distribution. That's why we model so many things in terms of Gaussian distribution. Okay, if we use any other distribution, a Laplace distribution is also symmetric with respect to the y-axis, but it would have higher entropy than the Gaussian. So if you have a number of variables, I'm digressing a little, but if you have a number of variables, then what was I going to say? You know the mean and the variance. That's all that's given to you. What distribution would you choose? Only the mean and variance are given to you. Mu and standard deviation is square root of variance, sigma. Mu and sigma are given. That's it. Choose the Gaussian distribution or normal distribution. Okay. That would minimize, from an information theoretic standpoint, the total amount of extra information that you're assuming. And we'll look at something similar to that. We will look at something, the maximum entropy method, later on in this course. Part B. Okay, now, since we don't know the variance, we'll assume that the variance is 1. Okay. Now, what about the covariances of the x's? Do you want to assume that they're positively correlated or negatively correlated? Again, without any knowledge, we'll assume that there is no covariance between them. All the x's are independently distributed. Okay. So, under these circumstances, this is the best assumption, prior assumption of the distribution of x. It's distributed around the origin, each of these x's independently, and this is the covariance matrix, the identity matrix. So the diagonal elements are the covariances, individual covariances between pairs of variables are 0, and these are all the diagonal elements are the variances or square of the standard deviations. They're all 1. Okay, so the probability of x is given by this expression. Okay, and I want to maximize the probability. So instead of, you see this, you have an exponential here. That's why I prefer to take the log. Instead of maximizing p of x, I'll try to maximize log p of x instead. Okay, same thing. I'll get the same solution. So I take the logarithm, and this is what I get. Log p of x I want to maximize. But what about this? This is constant, right? N over 2 log of 2 pi is constant. What is n? The dimensionality of x. Okay, so I want to maximize the log probability or the log likelihood. X star equals argmax p of x such that ax equals b, which is equal to, oh, I just wrote the same thing, log of this. Okay, I can neglect this term because it's not even a function of x. And so this is what I want to argmax. find an x such that it maximizes negative half x transpose x subject to ax equals b, which is equal to argmax under this same constraint of negative x transpose x. I simply drop the half. Argmax is finding the x. It doesn't change the x. It just scales up the value of the function, right? And I get rid of the negative by making it an argmin. Argmin x transpose x. So I want to find the min norm solution. This is x transpose x is L2 norm squared, right? So that's why I want to minimize the L2 norm of x squared subject to ax equals b, which is what I started off with. Minimize half x transpose x subject to ax equals b. Did you guys get that? Now, this is a very, very important point in machine learning, neural networks. In a neural network, now I'm digressing since we have a little time. In a neural network, you have a lot of layers. Between each layer, you have weights. Okay, and so there are so many solutions for the neural network that will do the job, but we would try to keep the squares of the summation of the weights at a minimum. That's what we want to also include in the neural network training algorithm. I'll show you all that later on. Okay.
I think that a regularization thing.
It's regular. It's basically what ridge regression.
Oh yeah, I did it. Yeah.
It's a ridge regression. Any other questions? Okay, so we can end this lecture